Okay, good afternoon. Welcome to the last session of this day. Thank you for coming in the afternoon. I'm going to talk about SQL Server transaction isolation levels. I'm Dejan Sarka. I am nearly 30 years in business, writing books, courses, etc., dealing with SQL Server for more than 20 years from version 4.2. And this talk is about transactions and isolations within SQL Server. So I do expect that you who are here do care about data integrity. So it's not like, about delayed transactions, not like about big data or whatever. It is about data integrity. So with transactions and with proper isolation level, we define the level of data integrity we are prepared to live with. And I will explain what these ACID transaction properties mean and what kind of bad dependencies can happen and what means pessimistic and optimistic approach, and then see and show in detail all transaction isolation levels supported by SQL Server. And then we'll also discuss locking, and I will show you what can happen with inappropriate level, too much locking, namely deadlocks. So ACID is a nice acronym for transaction properties. A transaction should be ACID. This is acronym for atomic, consistent, isolated, and durable. Now, this is completely made up acronym because the only relevant thing here is consistency. If database was in consistent state before a transaction, you want to have it in consistent state after the transaction. In order to get this consistent state, transaction must be durable, must not be lost. Okay? And also, transaction must be atomic, indivisible. Transaction can consist of more than one statement. So, for example, you insert a new invoice, you also want to correct automatically some stock level, right? And this must be done in an atomic way. So consistency, the need for consistency leads to durable and atomic transactions. And if you want to get transactions atomic, they must not interfere with other transactions, so they must be isolated. So you see, it would be enough that we would say just database must be in consistent state after the transaction, if of course it was in a consistent state before the transaction. Now what exactly consistency means? Well, this is defined by application or even better, by the business problem you are trying to solve. So if you don't care about any kind of consistency, if you can afford to lose transactions, then delayed durability is perfect for you, right? If not, then you have to define the level of consistency you need for your business problem. And application that requires appropriate isolation level to achieve this consistency. For isolation, we typically use locking. Though we'll see, we also can have copies of data to isolate updates from queries. Now, dependency model, what does it mean? Each transaction is reading a set of objects and writing a set of objects. And one way to ensure that each transaction reads consistent input and write consistent output is to run each transaction completely serially. First one, then second, then third, then fourth, etc. Turns out that unfortunately, this is kind of the only way to achieve 100% consistency. No bad dependency at all. To run transactions serially. Okay? Of course, this means serially on the same objects. Immediately we can have parallel transactions if they are dealing with part of the database, one and the other with the other part, of course. So with serialized transactions, input state is stable. Transaction is the only one active on this input state. It doesn't change while the transaction is running. And output can't interfere with inputs of other transactions. There is no other activity in this part of the database. So unfortunately, most of transactions do not share the transaction space. So we should do something better than this. So transactions can run concurrently if their outputs are disjoint from the union of the input sets. Okay? If T1 writes some object that's in T2 input or output set, there is a dependency between T1 and T2, expressed as T1 implies T2. So T2, we read this from right to left and say T2 is dependent on T1. Okay? Now, how do we schedule this transaction so we obey the dependencies? Typically, we start with locking to enforce these dependencies and use as few locking as possible to achieve as much concurrency of execution wherever it is possible. So for example, we have this kind of transactions. T8 and T7 are independent, and T7 depends on T5 and T6. T4 is independent of T5 and T6, but it's dependent on T2, and T5 is also dependent on T2, and T6 is dependent on T3, and T2 and T3 depend on T1. So with proper scheduling, we can achieve to execution of all of these 8 transactions in 4 time points. Okay? So equivalent serial model would be just one transaction after another. So we would need 8 time points for the same amount of transactions. Now when transactions are dependent, we can have the following bad dependencies: lost update, dirty read, unrepeatable read, and phantoms. I put phantoms a little bit more far away than the others because you'll see phantom is a kind of unrepeatable read. So what does it mean? We have now these 2 transactions, T1 and T2, and this is timeline, and we have initial state, an object, a column of a table if you wish, object X with value equal 10. Now transaction 2 read this X, and transaction 1 read this X. Transaction 2 updates this X, and transaction 1 also updates this X. Now transaction 2 writes it, and transaction 1 also writes it. And of course, transaction 1 wrote the same its own update after transaction 2. So this update, X equal X plus 10, was lost. So this is lost update, which is by ANSI standard forbidden for relational database management systems. So maybe did you visit Bob Bushman's talk about delayed durability or his pre-con seminar? So we get delayed durability in SQL 2014, which means that this is not in accordance for standard for relational database management systems. So we can get lost update with delayed durability in SQL 2014. Basically, it is forbidden for relational database management system. And this is really a bad dependency. So you probably don't want to have this kind of bad dependency in your line of business application, right? It simply means that SQL Server is going beyond supporting just line of business application. By the way, yes, of course, transactions and constraints do slow down updates, and this is the price you pay for data integrity. So yes, NoSQL solutions, big data solutions can be faster for the price of data integrity. SQL Server is like in the relational world, more or less mature product, so it tries also to cover more and more space in non-relational world, okay? And of course, this means that if we forget for a moment on this delayed durability, it means that in a relational database management system, you simply cannot get rid of exclusive locks for updates. No way. If we comply to the rules, we cannot allow we cannot allow this kind of bad dependencies, so it means the first one that starts updating, this one for example, should put some lock on this object, and the second one should wait until the first one writes this. And then this update was, at least for a moment, part of the database, so it is not a lost update. Okay? Now, next problem is already allowed for relational database management systems. Still might be pretty bad for line of business applications. So next problem is so-called dirty read. So we have again the same starting point. We have two transactions. We have timeline, initial state, x equals 10. Now transaction 1 reads this x, and then transaction 1 updates this x. Because we are in a relational database management system, because we do care about data integrity, transaction 1 puts exclusive lock at this moment on this object. So it means transaction 2 cannot update it, so we cannot lose transaction 1 update. However, this transaction 2 writes this, but transaction 1 simply doesn't honor the exclusive lock. Behaves like exclusive lock doesn't exist. Okay? Like peeking through the keyhole, you know. So let's see what's the state there. And reads this x. However, transaction 1 didn't commit. So now transaction 1 decides to roll back. And now we have a problem. Transaction 2 is using the value that was never part of the database. So this might be still a big issue for line of business applications. You know, maybe one transaction is receiving some products on the stock. The other transaction is already selling these products, promising these products to customers, and then when you want to keep the promise, you find out that you don't have these products in the stock. So this is not such a big issue as lost update, but still you might decide that this is too much for line of business applications. However, as I said, this is already allowed in relational database management systems. And it gets even worse than this. I will show you later in the demo that with this kind of reading dirty reads, reading uncommitted data, you shouldn't even trust the number of rows you have read. Even this, you can read the same row twice, or you can simply skip a row. Basically, it means that select doesn't even try to put any lock on the same data. Exclusive lock, as name says, is exclusive, is not compatible with any other lock. So select doesn't even try to put any lock, otherwise select would need to wait till transaction 1 releases the exclusive lock, which means either commits or rolls back the transaction. Non-repeatable read. You see, each next problem is slower, smaller problem, but getting rid of it is more expensive in terms of concurrency. We are more and more approaching the serializable model. So to get rid of lost updates, you need to serialize updates. Now with dirty reads, we didn't even try to serialize an update and selects. Single update and multiple selects. Non-repeatable read. We still have the same initial state, two transactions, timeline, and object x that equals 10. Now transaction 2 reads it, and actually might even, and transaction 1 reads it, and both of them might even put some shared locks on this object while they are reading it. So they prevent updating the object at the same moment while they are reading it. And if some other transaction would update these objects, they would have to wait until the exclusive lock is released. But shared locks are compatible, so they can read at the same time. But now shared locks are gone. I read it, I don't need it anymore, so I release it. So now transaction 1 updates this and writes, transaction 2 cannot read it again because we have exclusive lock until the end of transaction 1. So now transaction 1 actually commits and releases the lock. However, transaction 2 is still running. So at this moment, transaction 2 decides to read the same data again. And now we have a problem. We read the same data twice in one transaction, and we get different values. So which one is correct? This is unrepeatable read, which is, again, smaller problem than dirty read, because how many times you do read data in the same transaction twice? However, you see, as soon as you go to optimistic level and you have a copy of data, let's say on client side in some ADO.NET dataset or something like this, then you need to expect that somebody updated the data while you were doing whatever on client side. In this case, typically you do need to read before write. And the phantom problem, this is somehow similar to repeatable read, because we will read the same data twice. However, now we are reading set of objects, set of rows, for example, based on some predicate. So we have here maybe last name and some rank, whatever, and we are counting rows where rank greater than 3. And we have 2 rows, Smith and Brewer. And this is done in transaction 2. Now, transaction 2 can hold the locks on this data. So how do I get repeatable read? Well, transaction 2 must hold shared locks immediately when it gets it to the end of transaction. So now I'm holding these shared locks. However, I cannot hold shared lock on a row that doesn't exist. So what happens if I read the same data again, execute the same query? Now the result is 3. And this third one is the phantom. Where did it came from? So you see, to prevent this bad dependency, it's not enough just to lock this data and hold the locks till the end of transaction. Of course, what can you do? How can you prevent inserting a new row? Yeah, you should go one level higher and lock the whole table. However, SQL Server has one additional optimization and can do index range locks. So if I have index on this rank, SQL Server would lock everything that is greater or equal to 3 and still allow inserts with values 2, 1, or 0 or lower. If I don't have index on this column, then I cannot know the order. So then I have to lock the whole table. And from the moment of the first time I get this data, read this data, till the end of transaction. And this is the last bad dependency. And if I want to get rid of all of these dependencies, it simply means I get a lot of locking. All selects are now locking data immediately when they read it, and keep locks to the end of transaction, and also keep locks on higher level. Either it is key range or it is table itself. So this transaction isolation level is actually called serializable, and the name tells you that now you have completely serialized transactions. The same object. You cannot read and update at the same time. So what is pessimistic concurrency and what is optimistic concurrency? Maybe it's kind of simpler to start with optimistic and define what does it mean optimistic. Optimistic means that you have multiple copies of data at the same time. So you have your source data and you make a copy of this data either inside SQL Server or on middle tier or on client side. All of this is optimistic approach. And then your user works on this data. And at some point, user decides now it's time to commit the changes. And here is where optimism comes into the game. And user optimistically expects that nobody touched source data in between while end user was updating it. And this is the point where you typically should do read before write. And you will see that in some cases, SQL Server can do this for you if you use SQL Server's optimistic approach. And pessimistic approach is the opposite. We have a single copy of data at any time. So at any time, we have just one copy of data just inside the SQL Server. And we are all working on the same copy of data. And once the data is locked, other users cannot perform actions. So selects are compatible. That's why the logs are called shared logs. However, updates and selects are not compatible. And of course, updates and updates are also not compatible. Right? And update conflicts can occur in optimistic level, not in pessimistic level. Update conflicts means data has been changed, right? While you were updating this on client side. These are all SQL Server logs. So let me briefly explain them. So basic logs are shared and exclusive, okay? And you see exclusive logs are not compatible with any other logs. Shared logs are compatible with most of these logs except of this that has some X that are somehow exclusive. Now, then we have these intent logs, intent shared, intent exclusive, shared with intent exclusive. So what are these logs about? These are logs that SQL Server puts automatically on higher levels. So imagine you have an exclusive level, exclusive log on a row. SQL Server will automatically put intent exclusive log on a page and on a table or partition, if you have a partition table, and log escalation on partition level, and then table if you have partition table, and then also on database. And this simply tells SQL Server that something is exclusively locked on the lower level. So if somebody requests, for example, exclusive table lock, tab lock hint, for example, can't get it, and SQL Server doesn't even need to scan all of the syslogs table to check whether this table has any logs on lower level. So this is just to speed up this kind of resolution of this kind of problems. So this is like internal information for SQL Server. Now, there is one specific log, update log. This log is one you have to explicitly request, and you request it in a select statement. So you explicitly request it in a select statement where, let me go back and show you an example where you would explicitly where you would explicitly use it. So for example here, let's say that this is the second application. You see, this was non-repeatable read. And the second application wants to be sure that nobody will update data in between while transaction is running. Okay? So the second transaction has intention that at some point it will update and request exclusive lock on this data. So, but on the other hand, this transaction knows that this update will happen in the future. So why not allowing others to read this data at the same time? So the second transaction will request explicitly update lock, which is compatible with shared lock. So first transaction can read it. However, first transaction cannot put exclusive lock because now we have update lock. So this exclusive lock must be moved in timeline after the second transaction releases update lock. Now second transaction is sure that it will be able to update and put exclusive lock on a table, on the object, and do the update without need to read the data again before writing. Can be sure that nothing has changed. Okay? So this is the example where you would use this specific update lock. And this is the compatibility matrix. So you see update log is compatible with shared logs. And as soon as you have some X, there is no way that this could be compatible with anything else, as soon as you have exclusive logs. So let me now show you some demos. So I go here, and I have quite a lot of demos because we have a lot of isolation levels. And I will explain them during the demos. So I am creating a very simple table with 3 rows, AAA, ID, and 3 second column, AAA, BBB, CCC. SQL Server's default is read committed, so I wouldn't even need to execute this statement. Now let me begin the first transaction, and I will select everything from this table. Please note that these queries are intended just to show isolation level. Of course, it's a bad practice to use in application select star from table. Okay. And let me check the logs here. What you see is that I have this intent shared logs. Okay. So this means this is this on database level. This is database ID 13. I know it. Which means that I am connected, so nobody can exclusively log this database. This is intent share. And this is, these are logs on a system database, and this is IntentDB, which was used to get this result. So these are not important. The only one that actually is important is this one. However, shared log was there just for a brief moment while I was reading. For a moment, take my word. I will prove you this in a second. Okay? So let me go to the second transaction. And if I use the same database, it will work even better. And let's now update this, just 1 row. Okay? Update works, shared logs disappeared. Even if they were, they disappeared. Let's see what this transaction has logged. And you see this transaction, I have cluster at index on ID, so I have the key, so I got key log exclusive, and then I get intent exclusive on page level and intent exclusive on table level. But there is already shared log on database level. From the other transaction, you get it immediately with first connection, so it means nobody can exclusively log database. How do you exclusively log a database? Drop. Okay, this is one option. The other option is big magnet besides the hard disk, yes. But there are also less harmful options. So alter database set single user is actually exclusive log on a database level. And you cannot just use this statement at the moment because I have shared log. But there is additional brute force alter database set single users variant. You say alter database name set single user with rollback immediate. So it simply means this is limited to sysadmins and only. So it means roll back all of current transactions and give me immediately exclusive log. I don't care what people are doing. Please note both of the transactions are running. So I'm going to the first transaction and I'm trying to read the same data again. And now you see that select is trying to put shared log. I'm simply waiting. I cannot read the data until the first transaction decides to do something. So I will release this log, and now immediately I read the data. Now let's set transaction isolation level read uncommitted. So now I'm allowing dirty reads. So starting point is the same as with previous demo. I read the objects and my shared logs are already gone. Or they have never been there, right? We'll see in a moment whether they have been or didn't. So second part, second transaction exclusively logs a row, intent exclusive page, table, and so on. Go back to the first transaction. Let's try to read this data again. wow, now you see select didn't wait. And I got exclusive lock, but select doesn't honor it. Select didn't even try to put shared lock. So I'm reading value XXXXX. And now, first transaction, unfortunately, decides to roll back. And what happens? Yes, I'm using a value that was never part of a database. Of course, if I read this again, no problem. I get this version. But I am using the value that was never a part of database. And unfortunately, this read uncommitted level is the lowest level you can get in SQL Server. So you get the least amount of locking and the least impact on performance. So actually, with this level, SQL Server performs the best. So that's why this level is pretty popular among developers. I'm fine if you know what you are doing. And basically, it's not important if you know. If your customers know what they get with such an application, then I'm fine. So far, we have read a value that was never a part of a database. But it can happen also something else. I'm writing a lot of books together with Itzik Ben-Gan, so this part of code belongs to Itzik Ben-Gan, and thanks to him. So this part with skipping a row or reading a row twice was written by him. And let's create a table which has, in this case, unique identifier column, and I'm using new ID function to generate a GUID. So GUID should, the name tells you it's globally unique identifier, right? So it shouldn't repeat. Okay? Now, are GUIDs really 100% unique? Actually not, you know, there is some hash algorithm behind, and hash algorithms do not guarantee uniqueness. You know, but the probability that you will get duplicate GUID is so small. I mean, it shouldn't happen to you in before, I don't know, 100 billion years. So if it happens to you, you should, you know, stop going to casino. You already used your luck for this life and for a couple of, if you believe in reincarnation, also for a couple of next lives. So I'm creating unique cluster at index. Okay, it will even work better if I actually execute the code. And then I can create a unique cluster at index. Klaus, did you already have a session about using GUIDs? Yes. Okay. Okay. This is just for a demo, so please. But you know, sometimes, okay, to be a little bit mean, sometimes you simply cannot avoid GUIDs for indexes. You know, if you use index on last name and you are in Poland, you know, they are actually using GUIDs for their last name. At least it looks like this to me, you know. Okay. So what I'm going to do in this first session, I will simply insert these default values in a loop. Okay? And I got just unique identifier and one filler. So the point here is to get only a couple of rows in a page. So I will get faster this problem, reading the row twice. So I'm inserting this, right? And while I'm inserting this, I will go to the second session, and I will read all of the data into a temporary table with no lock, which is actually requesting read uncommitted level in the second transaction. So this select will not even try to put any shared locks. And then I will just check if exists any GUID that repeats more than once. I will break and show these GUIDs here. Okay? So, to speed up, let me just prepare everything. And here I will start my loop and start inserting. And now, wow, it happened nearly immediately. I don't need so much preparations. This one is still inserting. I can stop it, right? But you see, how many rows were read twice nearly instantly. So what happened? Well, I have clustered index, and GUIDs are approximately random. They are not statistically random, not random enough to be statistically random, but approximately random. So, because I have clustered index, SQL Server tries to insert them in the correct place, in the correct page. And if page is full, that's why I have this filler. Then page split occurs and the new page is moved somewhere physically where there is free room. And I'm scanning the data, right? I just read this row, and now some of the rows were moved to a new page. So when I come with my reading to that point, I'm reading the same rows twice. Right? Definitely, I mean, it's not possible to get so many duplicate GUIDs. Even in Poland, you can get so many duplicate last names. Okay, let's leave now Poland for a moment. Okay, now let's see the opposite example. So this is very, very similar table, just it has also sequential value. Unique identifier, filler, and sequential value. From unique identifier, I cannot conclude that I have skipped it. But we will find sequential values that were skipped. So, let's create clustered index. And let's also create manual sequence. So I'm creating table called sequence that will hold sequences. And insert the first value. And in my first connection, let's be sure that we start from empty state. So I will just update my sequence, raise it for 1, and immediately, you know, this update syntax, this is very efficient. So I update the sequence, and at the same time, I'm reading the new value in a variable, so I don't need to network round trips for this. And then I am inserting into my table sequential value. GUID is created automatically, and filler has a default constraint, so it's not important. So I'm doing this in a loop, endless loop, and in the other transaction, I'm checking the maximal sequential value, and then I'm again selecting everything from my T1 into temporary table with no lock. Even to speed up queries, create clustered index, now this time on sequential value. And now I'm simply checking, I'm reading data. You see, first I'm limiting to read only this data that is max, where sequential value is lower than current max. So I prevent new inserts to interfere with my analysis. And now I'm selecting minimal sequential value that doesn't have a following value. So I'm searching for a value that simply doesn't have the value which would be 1 bigger than current value in this temporary table. Okay? So let me prepare everything, and then when I get this, I will simply show the results. So let me start filling the first table and updating the sequence. And you see, I immediately get some results, so I can stop the first query, and let's see what happened. Well, value 14,198 doesn't have the next value. And of course, this value does exist in the original table. It's just that I skipped it. This was the opposite problem. I was reading, doing the full scan, and the other transaction was inserting data. So I was maybe somewhere here, and because my clustering key is GUID, some new insert went here. And then another insert came to the same page, and page split occurred, and this was moved somewhere else. So when I came to that page, the new row was actually missing from that page, so I never read it. So you see, with this read uncommitted level, you shouldn't even trust the number of rows you have read. So it's worse than most of developers expect. Okay? It's worse than most of developers expect. Now let me go to the repeatable read level. I started with read uncommitted because it is default, you know. In the slides, with read committed. In the slides, I started with read uncommitted, but this is SQL Server default, so I read committed, so I decided to start with the default. Now I have repeatable read level. So what happens now? You see, I'm reading just one row with a predicate, and I'm actually getting logs, shared logs on this row. And now remember, with read committed, the shared log disappeared. So we had to conclude that it was there for a brief moment when we tried to read data that was exclusively logged. Now we can see it because now it's held to the end of transaction until rollback or commit. And of course, I also have intent shared on the page level and intent shared on the table level. I'm looking only for those with database editor thing. These are the ones that are interesting here. Let's hope this will remain like it is for next 40 minutes. Okay, so let me go now to the second transaction. And first, please note that the first row is locked. Okay, so row with key 1. So I can insert a new row. Not a problem here. I can insert it. And I get exclusive lock on this new row. A transaction never blocks itself, so I can even read everything. So I can see the new row and also this row that has a shared lock in the first transaction. Now, let's go here. We still have these shared locks, right? We still have shared lock on this row. So let's try to update this row. And now you can see that because there is a shared lock, update has to wait. And by default, it waits forever unless we set lock timeout. So by default, it waits forever. So please take care not to start a transaction and then put some user interface, you know, and then leave end user to do whatever and finish when the end user clicks OK. Now this means forever. So, you know, end user can go in between for lunch. On the way back, he is hit by a truck and so on. You know, shit happens. But what I've got is read consistency. I can read the same row as many times as I want, and it will never change in the same transaction. Now when I roll back this, so I release my shared lock, update went immediately through. Okay? So I can see that now this row is updated, right? And now I can roll back a transaction. Now let's go to the serializable level. Serializable. And I'm requesting this, it's enough to request it in single transaction. This transaction requests serializable level. So I'm beginning a transaction and I'm counting rows where text column is between A and C. Okay? These are three rows. Let's see the logs. Well, what you see now are these interesting logs. So I have range shared logs. I have range shared logs. So anything after CCC could be inserted or before AAA, but not in between this range. So I'm holding shared logs, and I'm holding the shared logs till the end of transaction. So let me now go to the second one. Begin it. And let's try to insert this value which is between A and B. wow, you see, now already insert is blocked. So the whole key range is locked, so I cannot insert a new row in this key range. I simply have to wait until this transaction finishes, and this transaction has now completely stable input. As long as it lasts, it will always read the same rows. It will not get a phantom, and of course you can imagine that also you cannot delete a row from this range at the moment. So let's roll back it, and of course insert went immediately through, and of course this insert now has left exclusive lock and intent locks and so on. And yes, it exists now, this row, and also I can update, right? And of course I will roll back a transaction. So these were all pessimistic levels. Now let's go to the two optimistic levels. And please note that I changed the database context in one connection. The nice thing about first optimistic level, read committed snapshot level, is that you get it with a single command. So this is probably the best, let's say, quick and dirty option to get rid of locking problems, or to get rid of majority of locking problems without modifying the whole application. Now this might be very expensive. Please note that in longer terms, if you have a lot of deadlocks or even too many wait locks, you might decide that you need to rewrite something. But this is quick and dirty solution. Read committed snapshot. It's quick and dirty because this is a single alter database command. Set read committed snapshot on, and this is read committed with copies of data created automatically by SQL Server. The only prerequisite is, this will not end well, the only prerequisite is that you must be the only one in the database while you are executing this alter database command. So now I can see from these databases whether this is read committed snapshot. Yes, this is the one. I don't even need to set this default transaction isolation level. This is read committed with snapshot. And I will explain how it works during the demo. So let me now I can go back in the context of SQL 2012 database. So now I'm starting the first transaction. Okay. Selecting. Great. Please note that select doesn't even leave any lock, not even for a short time. Although I have read committed level. What select did is select actually enrolled this transaction in active database snapshot transactions. This is one of the, this is a dynamic management object with one of the longest names. CSDM tran active snapshot database transactions. So select enrolled itself there. So now SQL Server is informed that somebody is working on snapshot level. Select didn't even try to lock the source data. We still have only a single copy of a row. We can check sysdm tran version store and see that there is nothing there. So we still have a single copy of row. Now let's go to the second transaction and begin it and update this table. This is working on the source data. Update is still leaving exclusive lock on the source data. However, this transaction is now also enrolled. You see session ID 59 is also enrolled in the list of active snapshot transactions. And let's check the version store. Sorry. Let's check the version store. And now I have one row in this version store. So where is this version store? this is actually in temp.db. So update, just before updating the source data, made a copy in the version store. Okay? You can imagine that there is a price for it. But select doesn't need to lock it anymore. Select will go and read this data from the version store. So select doesn't need to even try to put the shared lock. Okay? So let me go to the first transaction. Select all of the data again, and I get the old state. You see, I actually updated this row, so in this second transaction, I get XXX in the first row. While in the first transaction, I still get the old state. Select is driven through old version. Now, I can even commit. And what happens now? Now the actual old version disappeared, and I got unrepeatable read. Please note that this is still read committed. So I read the same thing twice, and I got unrepeatable read. Let's check the version store. What do you expect to see? Nothing, of course, but this is done asynchronously. So actually, this is already marked for delete. Just the actual delete from version store happens asynchronously, so that's why I don't see it. So in a couple of seconds, or like in a minute, it will disappear also from here. So this is kind of statement level consistency. Now let's get back to the source, to the initial state. So I'm updating this to AAA again. Let's see if this has already disappeared. At some point it will be. No, these are the two transactions. Let's see the store. Okay. At some point it will disappear. At some point it will disappear. I don't see it anymore. But please note that what I had was unrepeatable read. So let's try this differently. What does it mean, unrepeatable read? Let's try this differently. I'm reading this, I'm getting AAA, select is not leaving any logs. Okay, come on, go away at some point, because I want to, yeah, the first one is already out, and the second update is still there, but you see, the second update when I get back to initial state is still there. So it's done asynchronously, I can continue, okay? So I will go here and update this to XXX, and again, I am doing the update in place in the source data, I'm locking this row, and I don't lock myself, so I see the initial state. The second the updated state. The second transaction doesn't issue any shared locks, goes to the old store, so I see the initial state, no problem. But now I commit, and the only difference between this and the previous demo is that now I decide that I will update. And please remember, it is committed, there is no exclusive lock, and the old version has disappeared. And now I'm issuing an update, and there is no update conflict. It is not repeatable read. So this is not a problem for SQL Server. Please note that this might be a problem for your application. So in this case, similarly like if you copy this data in avio.net dataset, in this case it is up to you to read the data before write and decide what to do. This is what you requested. Read committed, not repeatable read. And of course we have even higher isolation level, snapshot isolation level. So first, let me go to the second session, change the context to some other database to set read committed snapshot off. Let's see if at some point this version store gets empty. Yes, now it's empty because now I need it empty. Great. So now I can go back to my T-SQL 2012 database in the second connection, right? And go to the first one and alter database. First you must allow snapshot isolation. This is just allowing, not using it automatically. So it means you still have to request it. The only level that is used automatically is read committed, no matter if it's snapshot or no snapshot. Okay? So first, let's check if this database now allows snapshot isolation. Yes. And now I must explicitly request it. So I'm requesting snapshot isolation level. Now let me go and begin transaction and select, right? And check logs, no logs by select. Nothing in this is top version generators. I can check which transactions generate the most data in temporary store, in this version store, which is empty for the moment. Let me go to the second transaction, update something, and of course update logs the data. And the first transaction gets still the old data. Let's now go to the second and let's do the commit. So what happens is that I already have this new data. I committed this change. However, I still see the old version. This is a transaction level snapshot. It didn't disappear when the update committed the value. It will disappear when the last transaction that requested snapshot isolation level is committed or rolled back. So this is the only one, so this is also the last one. So now I can commit or roll back this transaction, and now the version store is cleared. Of course, again, it is cleared asynchronously, so there is still this, but you see, it actually was active till the end of the last transaction that used this data and requested snapshot isolation level. So let's revert this to initial state. And let's try to produce update conflict. So now I got initial state. Begin transaction, select, great, got initial state, check the logs, everything fine. Go to the second transaction, update the data, check the logs. Again, we are updating the source data, right? Data is updated, fine. I still see the old data, no problem. This will be there till the end of the second transaction. But now I commit. So now I commit, and let me check the data. I still see the old data. So now I have two versions, you see. I have AAA in temporary store and XXS in the actual table. So let me now try to update this to YYY. And you see I get this error. So update conflict was automatically resolved by SQL Server. So in your application, you should be prepared to catch this error, which is one of the errors with the longest error message. Everything with this snapshot isolation level is long. So you should be prepared. It's very descriptive. You know, many times these error messages really don't give you enough clue. I love the one, you know, I got not so long ago from analysis services in multi-dimensional mode suddenly crashed, so I went to Windows application log, and the error was not a Windows application. So very, very informative. What the analysis services is at some point not a Windows application. Anyway, this is more descriptive, right? So you get data. So we have update conflict, and transaction was rolled back. So this first transaction was rolled back. So what happens if I try to execute rollback? Of course, it's already rolled back. So I don't have any transaction anymore. So let's go to initial state, okay, and go here. And let me go back to the slides. Okay, I will not go into details here. This is one of the most important things to do troubleshooting. You have a lot of dynamic management views, you have additional procedures. Troubleshooting blocking locks, okay? How do users perceive blocking locks? Waiting. They perceive this as performance problem. They are waiting on something. These blocking locks, wait locks, are not really problematic. I mean, you should keep transactions as short as possible. And definitely, as I said, I cannot go in a single session through everything, but if you need to learn more about these performance issues and blocking and so on, we have Klaus here. So he's also having a workshop in London in May about this. So let me go further continue with this presentation. Lock escalation. You see SQL Server tried to lock the rows to go to the lowest possible level. However, each lock means inserting in a row in some system table which is held completely in memory. So you can imagine that at some point this system table would use all of the memory just to control the locking. Of course, this makes no sense. So we have locking escalation. So SQL Server will automatically escalate if you have too many locks on a higher level. Right? So from row, next higher level is table, not page. You have to request page locks by yourself, either with alter table or with query hint, unless you have a partitioned table. Then SQL Server can stop escalation on partition level, and this could be extremely useful for very large tables with big updates. You see? So what can happen is something like this. Let's say that I have this big table, and one update is updating these rows, while the other update is updating this set of rows. So I get row, 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 row lock, and now I break the threshold. Okay? So this will try to put exclusive lock on table. However, I already have intent exclusive because of this transaction. So this is now wait lock. But this is updating, 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 and now it tries to put also exclusive lock here, and now I have a deadlock. And partitioning can help me here. If I split this in partitions, then this will be escalated here, and this will be escalated there. And I can perform two huge, large updates at the same time. Now, the other option to prevent lock escalation is to request page locks, because you have multiple rows on a page. So you lock the whole page, and you have less locks. Still, lock escalation can happen, right? If you are locking more than 5,000 pages, then SQL Server will escalate locks. Again, to table or partition level. Okay. And of course, there are also some trace flags which you can use to completely prevent lock escalation. And this could be very dangerous, you know, because then you are holding all of the locks in memory without escalation. So this might be very, very problematic. So isolation levels, you saw, determine consistency of requested data and concurrency. And this is just a recapitulation of the demo. So this is more or less, this next slides are more or less just for me to remember, to see if I forgot to mention something during the demo. I'm getting old, and if something is not written, this doesn't exist for me, sorry. Let's see. So yes, we mentioned isolation levels based on row versioning, snapshot and read committed snapshot, which are supported as of SQL Server 2005. And we saw that this can be set on isolation levels can be set at session level or at query level with specific hints. And this is metrics showing isolation levels and what kind of these bad dependencies they do allow. And yes, read uncommitted, which is the lowest, is the cheapest in terms of locking, but it allows dirty reads. You see, cheapest because also creating this version store costs something. Typically less than locking, you know, because many times it's very simple to optimize TempDB. You can just put it on SSD or on RAID 0 array of SSDs combined in RAID 0, and that's it. And you get better performance. And this is, you know, setting transaction isolation level to read committed snapshot is really probably the best quick and dirty exit if you have a lot of blocking and deadlocking problems. This is the easiest. I'm not saying you should use this all over. It's better than using no lock hints or read uncommitted because at least you get, let's say, consistent data. But in longer terms, you should check why you have so much locking. Now, even worse than wait locks are deadlocks. I have shown you one example how deadlock can occur. Now I will explain other possibilities how a deadlock can occur. And deadlock is, of course, worse because one of the transactions involved in the deadlock is rolled back automatically. So it means you did some work, and then you roll back this work, and now you have to do it again. So in this case, let's say these two transactions were involved in deadlock. One would be selected as a victim, rolled back automatically, let's say this one. All of these updates have to be rolled back. So this one was maybe already working half a minute, and now another half a minute for rollback, and then you have to repeat the transaction. What other deadlocks can occur? I hope that only locks will be dead by the end of this transaction. Nothing, nobody else. I mean, I'm a good candidate for a deadlock here with these wires. Okay. So, what other deadlocks can happen? This is very typical, called simple or also cycle deadlock. So you see, first transaction is updating table 1, while the second is updating table 2. And then the both transactions, you can imagine imaginary timeline going down, right? Vertical one. Now the first transaction is reading from table 2, and table 2 is exclusively locked. So I got a wait lock so far. However, now this one is trying to read from table 1, and now I get a deadlock. Now I simply get a deadlock, and SQL Server will select one of these transactions as a victim, typically the one with the lower cost, you know, that did less work, less updates. Okay. This is slightly different version of cycle deadlock. Now I have updates in selects with predicates. However, unfortunately, these predicates are not supported by an index. Okay. So I'm updating T1. Let's say that this is unique index on column 1, so I'm updating this row. However, because I don't have an index, I have to put exclusive lock on a higher level. Sorry. And I'm updating table 2, and maybe this is also an index. Also, it's not supported by an index, so again, I'm leaving exclusive lock on a higher level. Now I'm reading something different from table 2. The row where column 1 equal 20 was updated. However, I'm reading a row where column 1 is equal to 10. But because I don't have predicates supported by an index, I have exclusive lock in T2 on a higher level, so select is blocked. This select is reading from table 1 where column 1 equals 20. And remember, the only row that was updated was the one where column 1 equals 10. However, this predicate is also not supported by an index, so it means this is also blocked. And because both transactions are blocking each other, I get another deadlock. And now this is more complex picture, which is showing how you can get a deadlock on a single table. And how many of you have attended Klaus' session about bookmark lookups? Yes, Klaus did. So this is the same example as Klaus have shown. Just he called it bookmark lookup problem, but it's the same thing. I will not call it anyhow. So we have different name. Okay, deadlock with a single table. He said.
We are from different countries.
Yeah. Okay. Anyway, this is the same thing. So let me explain how it goes. So you see, I have here clustered index on column called key call, right? And I have a non-clustered index on column called column 1. And here I'm updating the table, set column 1 equals new value, where key call equals 2. So this is time point 1. Point in time 1. I was expecting to see TP1 there, but it's PT. Okay, so it's a point in time 1. Time point 1. And in this time point, we are putting exclusive lock on this row where key call equals 2. And this is granted. No problem. We are in a clustered index. Now this one now wants to select column 2 from T1 where column 1 equals 102. Please note that this query cannot be covered with non-clustered index because non-clustered index is on column 1 and includes also key call from clustered index, but not column 2. Okay? So we will need bookmark lookup to please close. We will need a bookmark lookup. So what happens? In time point 2, I get shared lock on non-clustered index where column 1 equals 2. So at this moment, I have exclusive lock in one row in clustered index and shared lock in one row in non-clustered index. Now, in time point 3, I need to update non-clustered index because I actually updated column that is key for the non-clustered index. So now, my first transaction is trying to get exclusive lock on the same row where I already have a shared lock. So at this moment, this is a wait lock. But because this was not a covering index, I need to use bookmark lookup to find column 2. And now I'm waiting for shared lock here, and I'm getting a deadlock. You see? So this is this example of bookmark lookup deadlock or deadlock with a single table. Now let me go to the second part of the demo. And show you a couple of examples of deadlocks. So I'm creating two tables. And you see I have key call, column 1, column 2. Inserting values 1, 2, 3, 101, 102, 103, ABC. And I have similar structure on table 2. And inserting different values. Keys are 1, 2, 3, but different values 201, 202, 203, and XYZ. So this is my state. I have 101 and 201 in table 2 and ABC and XYZ in the second table. Okay? So let me begin transaction and update T1. Set column 1 is column 1 plus 1 where key call equals 2. Okay? Second transaction, update T2. So I'm updating a different table, okay? First transaction now wants to select from the second table and it's blocked. I see it's blocked. Now second transaction selects from the first table and it's also blocked. And one of these transactions will be selected as a victim of a deadlock resolution process. So this one has to be rerun. And this one, of course, doesn't exist anymore. This one can be committed. Which one was selected? You see, in this case, both transactions perform the same amount of work. Then SQL Server will select as a victim the one that started later. And if both starts at the same time, then the victim will be the one that connected later, which simply means has bigger server process ID speed. So, deadlock with a missing index. I'm updating T1, set column 2 equals column 2 plus something, where column 1 equals 101, right? Now let's go to connection 2. Update table 2, again with a predicate. Now please note the predicate, I updated where column 1 equals 203. Now I'm reading completely different row, but I'm blocked because I have lock on a higher level. And here I'm reading from table 1 from completely different row, but I'm blocked on a higher level. So again, one of the transactions should be at some point selected as a victim. Again, in this case, we had transactions with the same amount of work, but I opened this connection later and started this transaction later, so this one was a victim. So this one can still be committed, while the second one, of course, doesn't exist anymore. Now, let's create indexes. Column 1 on T1 and on T2. And let's repeat this. So let's update this in connection 1. Update table 2 in connection 2. Select from table 2, but different row. And just to be sure, I'm not saying you should use index hint. I have to use it, you see. SQL Server might not even bother to use index seek because I have only 3 rows in a table. So index seek might be even slower than table scan. But you see, select was not blocked at the moment. And the other select from second transaction from table 1 is also not blocked. And I can commit both transactions. And let's update this to initial state. Now I will constantly update this column 1. You know, these updates are so fast that it's kind of hard to get this single table deadlock with one simple update. I'm not fast enough, so I'm doing constant update, changing the values, right? And in the second transaction, I will do the constant select. And I'm selecting column 2, which is not part of the index. But I'm working on table 1, and here I'm updating table 1, so I'm working on the same table. This is key of the non-clustered index. So let's start it. And let's start this one. And let's wait. In this case, you see, already got a deadlock. And in this case, I didn't even need to guess which one will be selected, because this one is not actually performing any update. This is more reasonable to select this second transaction for a victim. And should be good that at some point I stop this, this loop. Okay? So, we are coming slowly to the end of these demos and presentation I prepared. So you see, what we explained is all isolation levels in SQL Server with data consistency. As I said, in SQL 2014, with delayed durability, you can even get lost updates. So all isolation levels that pertain to the relational database management system part of SQL Server. And basically, you see, getting rid of these bad dependencies means going towards serializable level. So you should check what kind of level you need for your specific business. I'm not saying you shouldn't use read uncommitted. This is the cheapest level. Okay? I'm just saying that it's overused. You have also read committed snapshot, and at least you get consistent data. Read uncommitted if you do not care about amount of rows read, about dirty reads, fine. But please inform your customers that this can happen. Otherwise, as I said, it's up to you to define the correct isolation level to fit with your business problem. So any questions? Yes, please.
I only recently heard this week that transactions begin at the first statement after the begin transaction, not at the begin transaction.
The question is that transactions actually start with first statement after the transaction. Depends how you define what does it mean start. You cannot lock anything before you execute the first statement. But begin transaction goes immediately to transaction lock. So considering locking, begin transaction doesn't really start locking, let's say. But transaction has already started because it already got ID, so it's already there in transaction log. Begin transaction is immediately written in transaction log. But locking happens only after you use some data. The question is, the survivor of deadlock resolution process would be the one that started first if both the cost of updates of both transactions is equal. Yes, this is default, right, Klaus? Yeah, right, he didn't. So it's right, he doesn't listen, and I can talk whatever I wish. This is pertains, yes, very good question. What does it mean, which one started earlier? The one with begin transaction that started earlier. So actually you see transaction starts with begin transaction. Locking starts when you execute the first statement. Yes, please?
That last example, you made it use the index. If you hadn't done that and it hadn't used the index, would you have had a different type of lock?
You see, if I wouldn't use the index, I would get different kind of weight lock, because query optimizer might decide to do a table scan in this case. So I would get a weight lock on the row that was locked.
Right. So if you're writing stuff that relies on it being the index level, you need to sort of force it to make sure it does use it.
No, I force this usage because I have so small table. So you see.
Yeah, but I might in the real world I might have a small table that gets with it.
In the real world, you know, you would probably have enough rows to get indexing automatically by query optimizer.
Right.
But in this case, I wanted to be sure that this index should be used. Think of query optimizer works on page level. So this whole table is less than one page. It fits in a single page. Index has immediately root level and leaf level. So index seek means 2 pages. So in this case, index seek was more expensive than table scan. And with table scan, I would actually get different kind of weight lock, not even a deadlock. So that's why I forced index seek. But in real production, you would have enough rows that index seek would be much cheaper if you are seeking for a single row. Sorry, what did you? if it would be a reference table, if it's too small, yes, it might happen that query optimizer would decide. But depends also, it takes into account also locking needs. I just wanted to be sure. Doesn't mean that you have to use this in production. It will take into account also locking needs. But anyway, let's imagine that you have repeatable read level and there are no locking needs, then SQL Server might decide to read the whole table. And then suddenly somebody starts update and it's blocked. Anything else?
When would you use the read uncommitted? If you can't be sure of anything, you just...
When would I use read uncommitted? I would try to use it as rarely as possible. Unfortunately, this is overused. This is like first exit that developers do when they get blocking problems and deadlock problems. This is very typical. Let's put with no lock hint everywhere. Now, imagine business problem. Let's say that you have a nervous manager, you are selling something, and you have a nervous manager that wants to check total sales every minute. So, of course, this manager is reading the whole table. And, of course, if you use some higher level, you have a problem because you will get less and less sales because, inserts and updates will be simply blocked. But for the total, you need something over the top. So if it's not exactly correct, it's good enough. So for example, in this case, this could be a solution. You know that you are approximately there, but you don't care if this is 3 pounds more or less. Depends again on your business. If you are selling aircraft carriers, then this one row might mean a big difference, the one row that is missing. But if you are selling orange juice, who cares if one is missing?
There's no way to prevent developers from using that? I mean, on the database or server level?
Well, how to prevent developers to use this? There is no way how you could, let's say, forbid this isolation level. So this is also hidden in the code. So you cannot really prevent it. The best thing.
With no lock effect, you can do it with policy-based management.
Policy-based management, that you catch the events that have no lock hint. Okay, and then roll back this. Okay, so it's kind of doable. But this is also. Yeah. So you make policy-based management based on string, substring of a string. So if you catch substring no lock, then you roll back this transaction. But then you have to hope that there is not a column which would be called no lock. And this can happen more frequently than you can imagine. I actually maintained some internal Microsoft database where columns were called select and update. Seriously, these were the names of the columns. Anything else? Okay, so thank you very much for coming to this session and enjoy the rest of the conference. It's dependent on T2, and T5 is also dependent on T2, and T6 is dependent on T3, and T2 and T3 depend on T1. So with proper scheduling, we can achieve to execution of all of these 8 transactions in 4 time points. Okay? So equivalent serial model would be just one transaction after another. So we would need 8 time points for the same amount of transactions. Now when transactions are dependent, we can have the following bad dependencies. Lost update, dirty read, unrepeatable read, and phantoms. I put phantoms a little bit more far away than the others because you will see phantom is a kind of unrepeatable read. So what does it mean? We have now these two transactions, T1 and T2, and this is timeline, and we have initial state, an object, a column of a table if you wish, object X with value equal 10. Now transaction 2 read this X, and transaction 1 read this X. Transaction 2 updates this X, and transaction 1 also updates this X. Now transaction 2 writes it, and transaction 1 also writes it. And of course, transaction 1 wrote the same its own update after transaction 2. So this update, X equal X plus 10, was lost. So this is lost update, which is by ANSI standard forbidden for relational database management systems. So maybe did you visit Bob Oshman's talk about delayed durability or his pre-con seminar? So we get delayed durability in SQL 2014, which means that this is not in accordance for standard for relational database management systems. So we can get lost update with delayed durability in SQL 2014. Basically, it is forbidden for relational database management system. And this is really a bad dependency. So you probably don't want to have this kind of bad dependency in your line of business application, right? It simply means that SQL Server is going beyond supporting just line of business application. By the way, yes, of course, transactions and constraints do slow down updates, and this is the price you pay for data integrity. So yes, NoSQL solutions, big data solutions can be faster for the price of data integrity. Now, SQL Server is like in the relational world, more or less mature product, so it tries also to cover more and more space in non-relational. Okay, good afternoon. Welcome to the last session of this day. Thank you for coming in the afternoon. I'm going to talk about SQL Server transaction isolation levels. I'm Dejan Sarka. I'm nearly 30 years in business, writing books, courses, etc., dealing with SQL Server for more than 20 years from version 4.2. And this talk is about transactions and isolations within SQL Server. So I do expect that you who are here do care about data integrity. So it's not like, about delayed transactions, not like about big data or whatever. It is about data integrity. So with transactions and with proper isolation level, we define the level of data integrity we are prepared to live with. And I will explain what these ACID transaction properties mean, and what kind of bad dependencies can happen, and what means pessimistic and optimistic approach, and then see and show in detail all transaction isolation levels supported by SQL Server. And then we'll also discuss locking, and I will show you what can happen with inappropriate level, too much locking, namely deadlocks. So ACID is a nice acronym for transaction properties. A transaction should be ACID. This is acronym for atomic, consistent, isolated, and durable. Now, this is completely made up acronym because the only relevant thing here is consistency. If database was in consistent state before a transaction, you want to have it in consistent state after the transaction. In order to get this consistent state, transaction must be durable, must not be lost. Okay? And also transaction must be atomic, indivisible. Transaction can consist of more than one statement. So, for example, you insert a new invoice, you also want to correct automatically some stock level, right? And this must be done in an atomic way. So consistency, the need for consistency leads to durable and atomic transactions. And if you want to get transactions atomic, they must not interfere with other transactions, so they must be isolated. So you see, it would be enough that we would say just database must be in consistent state after the transaction, if of course it was in a consistent state before the transaction. Now what exactly consistency means? Well, this is defined by application of the same row twice, or you can simply skip a row. Basically it means that select doesn't even try to put any lock on the same data. Exclusive lock, as name says, is exclusive, is not compatible with any other lock. So select doesn't even try to put any lock, otherwise select would need to wait till transaction 1 releases the exclusive lock, which means either commits or rolls back the transaction. Non-repeatable read. You see, each next problem is smaller problem, but getting rid of it is more expensive in terms of concurrency. We are more and more approaching the serializable model. So to get rid of lost updates, you need to serialize updates. Now with dirty reads, we didn't even try to serialize an update and selects. Single update and multiple selects. Non-repeatable read. We still have the same initial state, 2 transactions, timeline, and object x that equals 10. Now transaction 2 reads it, and actually and transaction 1 reads it, and both of them might even put some shared locks on this object while they are reading it. So they prevent updating the object at the same moment while they are reading it. And if some other transaction would update these objects, they would have to wait until the exclusive lock is released. But shared locks are compatible, so they can read at the same time. But now shared locks are gone. I read it, I don't need it anymore, so I release it. So now transaction 1 updates this and writes, transaction 2 cannot read it again because we have exclusive lock until the end of transaction 1. So now transaction 1 actually commits and releases the lock. However, transaction 2 is still running, so at this moment transaction 2 decides to read the same data again. And now we have a problem. We read the same data twice in one transaction, and we get different values. So which one is correct? This is unrepeatable read, which is again smaller problem than dirty read, because how many times you do read data in the same transaction twice. However, you see, as soon as you go to optimistic level and you have a copy of data, let's say on client side in some ADO.NET dataset or something like this, then you need to expect that somebody updated the data while you were doing whatever on client side. In this case, typically you do need to read before write. And the phantom problem, this is or even better by the business problem you are trying to solve. So if you don't care about any kind of consistency, if you can afford to lose transactions, then delayed durability is perfect for you, right? If not, then you have to define the level of consistency you need for your business problem. And application that requires appropriate isolation level to achieve this consistency. For isolation, we typically use locking. Though we'll see, we also can have copies of data to isolate updates from queries. Now, dependency model, what does it mean? Each transaction is reading a set of objects and writing a set of objects. And one way to ensure that each transaction reads consistent input and write consistent output is to run each transaction completely serially. First one, then second, then third, then fourth, etc. Turns out that unfortunately this is kind of the only way to achieve 100% consistency. No bad dependency at all. To run transactions serially. Okay? Of course, this means serially on the same objects. Immediately we can have parallel transactions if they are dealing with part of the database, one and the other with the other part, of course. So with serialized transactions, input state is stable. Transaction is the only one active on this input state. It doesn't change while the transaction is running. And output can't interfere with inputs of other transactions. There is no other activity in this part of the database. So unfortunately, most of transactions do not share the transaction space. So we should do something better than this. So transactions can run concurrently if their outputs are disjoint from the union of the input sets. Okay? If T1 writes some object that's in T2 input or output set, there is a dependency between T1 and T2, expressed as T1 implies T2. So T2, we read this from right to left and say T2 is dependent on T1. Okay? Now, how do we schedule these transactions so we obey the dependencies? Typically, we start with locking to enforce these dependencies and use as few locking as possible to achieve as much concurrency of execution wherever it is possible. So for example, we have this kind of transactions. T8 and T7 are independent, and T7 depends on T5 and T6. T4 is independent of T5 and T6, but okay. And of course, this means that if we forget for a moment on this delayed durability, it means that in a relational database management system, you simply cannot get rid of exclusive locks for updates. No way. If we comply to the rules, we cannot allow this kind of bad dependencies. So it means the first one that starts updating, this one for example, should put some lock on this object, and the second one should wait until the first one writes this. And then this update was, at least for a moment, part of the database, so it is not a lost update. Okay? Now, next problem is already allowed for relational database management systems. Still might be pretty bad for line of business applications. So next problem is so-called dirty read. So we have again the same starting point. We have two transactions. We have timeline, initial state, x equals 10. Now transaction 1 reads this x, and then transaction 1 updates this x. Because we are in a relational database management system, because we do care about data integrity, transaction 1 puts exclusive lock at this moment on this object. So it means transaction 2 cannot update it, so we cannot lose transaction 1 update. However, this transaction 2 writes this, but transaction 1 simply doesn't honor the exclusive lock. Behaves like exclusive lock doesn't exist. Okay? Like peeking through the keyhole, you know. So let's see what's the state there. And reads this x. However, transaction 1 didn't commit. So now transaction 1 decides to roll back. And now we have a problem. Transaction 2 is using the value that was never part of the database. So this might be still a big issue for line of business applications. You know, maybe one transaction is receiving some products on the stock. The other transaction is already selling these products, promising these products to customers, and then when you want to keep the promise, you find out that you don't have these products in the stock. So this is not such a big issue as lost update, but still you might decide that this is too much for line of business applications. However, as I said, this is already allowed in relational database management systems. And it gets even worse than this. I will show you later in the demo that with this kind of reading dirty reads, reading uncommitted data, you shouldn't even trust the number of rows you have read. Even this, you can read